Okay, friends, error approximations, my least favorite thing in this chapter, but it's okay. It's actually not too bad. All right, here's how it goes. Now, what I want you to focus on for a minute is the fact that on the first page, I am only talking about alternating series, okay? Ones that go plus, minus, right? On the second page, we will talk about non-alternating series, which are a little bit more difficult, all right? Okay, in an alternating series, if it's a converging series, right, so it's getting smaller, it's going to a particular number, we can approximate the sum by using the first n terms, so we're like doing, 10 terms or whatever. The error will be less than or equal to the n plus first term. Now, that sounds a little bit confusing, but n plus first term just literally means next term, okay? So we're just going to go until we get to the sum that it wants, and then the next term is the error approximation. So it works like this. All right, let me write 6 terms of this here. Okay, so remember you start by like plugging in 1. Now if I plug in 1, it's going to be negative 1 to the 1 plus 1. So negative 1 to the 2 is positive 1 over 1 factorial. Then I'm going to plug in 2. That's going to be negative 1 over 2 factorial. 3 is negative 1 to the 4th, so it's going to be positive 1 over 3 factorial. Now that I see the pattern, I can just go ahead and keep going. Negative 1 over 4 factorial, positive 1 over 5 factorial, and 6 terms. Negative 1 over 6 factorial. So we want to approximate the sums. This, by the way, is what's called a partial sum. Sometimes we could put like the part P for partial sum or whatever. So let's go ahead and figure this out. I think I'm going to have to go grab my calculator over here. Okay, so I'm going to go 1 minus 1 over 2 factorial. 2 factorial is just 2, something like that. 1 over 3 factorial is over here under probability, okay? Minus 1 over 4 math over, if you know these factorials, you don't have to go do them, plus 1 over 5 factorial minus 1 over 6 factorial. There we go. Boom. Okay, first 6 terms. So 0.63194, and then the 4 is repeating. Okay, perfect. So this is an alternating series. It says find the upper bound for the remainder for the approximation. Okay? Well, we just go to the next term, you guys. Now, the next term is 1 over 7 factorial. We're adding it, okay? So 1 over 7 factorial. So if I go and I type in, all right, 1 over 7 factorial, and I get that. Now, that's a little tricky to write, but it's going to be point. Remember that the E negative 4 means I go back 4 decimal places. Now, one of them goes past the 1 and then 3 zeros. So 1, 2, 3 zeros, 1, 9, 8, 4, whatever. That's probably good. Okay? That's my error. My error is less than or equal to that. Okay, because it's just like the next term, and it's adding that, and then it's adding, and then subtracting, adding, subtracting, adding, but it's all going to get smaller and smaller and smaller as we go. Now, find the upper and lower bounds for the actual sum of the series. Okay, let's write it like this. The sum of this series, negative 1 to the n plus 1, 1 over n factorial, is going to be contained within. Now, this is the sum, this is the error bound. I just have to add those, and that's the highest it will ever go, because this next term was plus, and then it goes back down to minus, right? So if I come on over here, and you guys know you can just click up and go that plus, whoops, that equals, that is the highest that this will go, okay? 0.632142. I'm putting extra decimal points on the AP test. They only look at the first 3. I'm just writing a few more. So that's my upper bound. Okay. Okay. Now, if we look for what the lower bound is going to be, well, if you think about it, you guys, okay, after this point, 63194, then it adds a little bit, and then it takes away even a little bit more, and adds, and it takes away, and adds, and takes away. But it's getting smaller each time. So this is like, this terms are never going to go below 0.63194. All right. So it's kind of like bounded in between there. So I don't know. I guess that's not bad because we've got it pretty close to the first, almost to the 10,000th place. That's not bad, right? Okay. Approximate that with an error of less than 0.001. Okay, I'm going to write out a couple of terms of this. Again, this time I'm starting at 0. A negative to the 0 is positive. That would be 1 over 0 factorial. When I plug in 1, it would be negative. That would be 1 over 2 factorial. When I plug in 2, it would be positive 1 over 4 factorial, negative 1 over 6 factorial, positive 1 over 8 factorial. Okay, so I'm going to like kind of test these terms to see, how far I actually have to go to get the error less than that. Well, I know 1 over 4 factorial is going to be too small. Let's start with 1 over 6 factorial, right? So I go on my calculator, I go 1 over 6 factorial. Okay, and this term is, let's write this here, 0.00138. So, if I only went up to here, that's not quite the best approximation because the next term, the error, I think I would have to go to the 8, right? Because this is not less than 0.001. It's a little bit more than that. So let me go to the next term now. Let me go to the 8. Okay, this is going to be like more than enough, but anyways, we'll look at it anyways. 1 over 8. We go over here. Factorial. Okay, that is plenty. Okay, so that term is 0.123402480. All right. That's amazing. So, in order to be with an error, of less than that, this is going to be my error, which means that essentially we're going to stop right here. Sometimes it'll ask you for how many terms. Sometimes it'll ask you whatever. And it wants me to like approximate this now. So I've got to do this. 1 minus 1 over 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial. I'm not going to go write it all down. So I don't need that term because that's going to be my good error there. And this is what it comes out to. You guys can type that in if you want, okay? But just so that we're like moving along here. All right. Now this is cool. Use an elementary series. These are the types of questions they like to ask, both on my test and on the AP test, to find the actual value of the series in example 4. Okay, do you guys remember the elementary series? I went ahead and grabbed a picture of them so I could, have it in my notes. Let's just put it over here for a minute and take a look. Okay, so we have ln, we have e to the x, we have cosine, we have sine. Which one does it look like? Obviously, it's e to the x, right? And it's e to the x if specifically x is 1, because 1 over 2 factorial, 1 over 4, 1 over 6, and even like the negatives and stuff match up. So we were going up to that point, but to find out like the actual thing all the way out to infinity, we'll just say that it's cosine of 1, because this is an elementary series for cosine, and it's cosine of 1. Now, when I go and type that in, let me make sure that I'm in radians here, which is what I want, and I just type in cosine of 1. This is what I get. Okay. 0.54030. Take a look at this approximation. That is a pretty killer approximation that we only had 4 terms for. And it definitely has an error of less than 1/1000. Okay, that's a very good approximation. So there we go. So here's a kind of summary of like where, like delete this picture. Okay, it actually, alternating series remainder is really all you need to know the error is less than or equal to the first unused term. It looks really complicated. It's just the next term, right? Now, remember, in our Taylor series that we're working with, okay, this is how we got, it's the, well, our Taylor series was this. The nth derivative at c, x minus c to the n over n factorial. This is just n plus 1, so it's the next term back. But if you're wondering where that formula came from, that's just our standard, Taylor series formula, and it's just the next one. Okay, now we move on to non-alternating. Nobody likes this one. That's kind of sad to say, but it is true. No, the Lagrange is just a little weird. So here's the main difference, okay? Because it's not alternating, it's still adding little bits, right? It's not just alternating. So it is slightly harder. It says, we call it Lagrange. All right. Okay, look. The only thing that's different is this. In fact, the only thing that's different is the fact that it says a z there. Okay, z is the x value between x and c, where it's y coordinate, so not z itself, but how high z goes. The value, let's go ahead and call this the value at z is a maximum. Okay, it's a little weird, but it's the n plus 1 term, but we have to make sure we're going to choose something that will maximize this derivative. Now, it might be at x, it might be at c, and it might be somewhere in between x and c. So it says it right here. Maybe at the center, it may be at x, or it may be somewhere in between. Every once in a while, actually more often than not, they'll give you something like sine and cosine, because we know sine and cosine have a maximum of 1, and so we use that, okay? All right, it says estimate e to the second using a Maclaurin polynomial of degree 10 for e to the x. Okay, where am I getting this from? So remember, it's, whoops, not that, boop, boop, okay, this. In fact, maybe I will be awesome and I will just crop this down so we only see the e to the x. Oh, that's killer. Okay, guys, here we go. So I didn't have to write that out. There's e to the x, okay? Degree 10 means that I need to go up here to x to the 10th, 10 factorial, okay? Now, I am approximating e to the 2. Yes, you actually have to go and do this. x3, whoops, over 3 factorial. 2 to the 4 over 4 factorial. And we do have to go up to 2 to the 10 over 10 factorial, okay? Now, if you're a really good typer, you can put out that all in and you can type it. Now, remember, if it's an FRQ, I mean, I'm just going like that because I don't have to figure out the decimal. But if it's a multiple choice or if we wanted the decimal, we have to type that in. Now, I do want to show you guys something on the calculator, okay? There is actually a place that we can do these summations, and it's under math. And if you scroll all the way down, it's under summation. Aha. Now, look at the general term of this, okay? We went out to the 10th, but look at the general term, you guys. X to the n over n factorial, okay? Now, if you actually want it to say n, you can go into mode and you can change this to sequence mode. Sequence is in series mode. And when I put my variable down here, oh gosh, how do I get out of this? Okay, there we go. And I put x, it'll actually show an n. Okay, very exciting. You don't need to turn it into that, but you could. Now, I am starting where n is, let's look at this real quick, okay? This is, n is 2, because it's 2 over 2 factorial, n is 3, that means n is 1, that means n is 0. So I'm starting at 0 and going up to 10, okay? I just wanted to check if I was starting at 0 or 1. So I'm starting at 0, I am going up to 10, and I'm going to make a fraction by going alpha y equals fraction, and it is let's see here, n over n factorial. Okay? And I'm summing that up. Now, that's actually e. Now, I want to do it for 2. And so, my new one, okay, so I actually just did the summation of e. With 2 being where the x is, okay, it's 2 to the n over n factorial. All right, that's what I was like messing up. This is like, I meant to go x to the n over n factorial, so I typed that in wrong, okay? Sorry about that. All right, I'm not going to go back and re-record because I make mistakes and it's all right. It's actually 2 to the n over n factorial, and then this is, I'm doing 10 terms. 2 to the 3 over 3 factorial, 2 to the 4 over 4 factorial. Yeah, that's perfect. And that's what that sums up to, okay? So it sums up to 7.38899. Now, do you guys remember what we were approximating? We were approximating, and this is so that I don't actually have to type in all of that all the way out to 10. You still could, but, you know, that's a little bit faster. What were we approximating? We were approximating e squared. My goodness, that is close up till the third decimal place. That's pretty close, all right? Now, use the Lagrange form of the remainder to estimate the accuracy of this. Of using this partial sum. So what's like the accuracy? Okay, so I always go like this. My Lagrange remainder is less than or equal to. Now, I know I'm going to the 11th, and then it's x minus c to the 11 over 11 factorial, because that's like next term, okay? Now, I am centered. Well, this tells me exactly where I'm centered. Maclaurin means you're centered at 0. And what am I using for x? I'm using 2. So this is x is 2. C is 0. Okay? And what I want to do is I want to find the maximum of the 11th derivative. Now this is like a little bit tricky, but let's think about what the 11th derivative is. Okay, now they gave you this because, I mean, going to 11 derivatives is like, bro, what? Except that this is e to the x. So what's the first derivative? E to the x. What's the second derivative? E to the x. What's the 11th derivative? E to the x. Now you have to have a little bit of background information on e to the x to know this. Okay, do you guys remember what e to the x looks like when you graph it? It's an exponential. It goes like that. Now remember, c was 0, x was 2. What is the maximum of this on the interval 0 to 2? Well, this is an increasing function, so it clearly hits its max right there. And what is the height of this function at 2? Remember, this is the function e to the x. So the maximum height that it gets is at 2 is e to the 2. Okay? So that's where you come in and you say, all right, this is e to the 2. Now, it's a little silly that, well, first, okay, before I talk about this, let's go ahead and go like type this in. So it's, not math, I was going to push alpha. Okay, it's a fraction. It's e to the 2. And then it's 2 to the 11th. Over 11 factorial. All right, and there we go. So this is my remainder is less than or equal to 0.0003791. Okay? That's what my remainder is less than or equal to. All right, now, what I was going to say is it's a little bit silly to find a remainder for e to the 2 for like a transcendental, because the whole purpose of using Taylor series is because, like, let's say we don't have a calculator, or Taylor series is how you program the calculator, right? Do you guys know what e squared is without a calculator? Like, I certainly don't, you know? So it's kind of funny to use e squared in the remainder of something where we're trying to approximate e squared because we don't know what e squared is. So it's like if we knew what e squared was, we would just use it and not have to approximate this. So that's a little weird. So every once in a while, I just want to give you a heads up on this. they'll say, well, let's say we don't know what e squared is. Well, since I know e is approximately 2.71, e squared is probably less than 9 because 3 squared is 9, right? Or I could even say it's probably less than 8. So like that might be better. Instead of using e squared, maybe I use an 8 or, since I know it's less than 9 or whatever. So sometimes we just like pick other numbers when we don't have an opportunity. But using e squared in the error for e squared is kind of like defining a word by using the word. That's like a weird way to do things. Okay? Okay, here's another Lagrange remainder. The fifth derivative of something is that if x equals 0.7 is in the convergence interval for the power series centered at 0, find an upper limit for the error when the fourth degree Taylor polynomial is used to approximate. Dude, that's a lot of stuff right there. That's a lot of information. But it did not tell me it was alternating. Now, a fourth degree Taylor polynomial, if I go next term for my error, I'm going to the fifth z, right? Now I need to find x and c. That was x, that was c. When this is centered at, we can just call that c. So then it's x minus c to the fifth over 5 factorial. And this is the only thing at this point I have to worry about. Okay, well, check this out. They gave us the fifth derivative. That was so nice of them. Sometimes they'll give it to us, like if it's something that's like too hard, they don't give us the original or something. Sometimes they'll give us a graph or whatever. So the fifth derivative is 700 sine x. Now a real fast way to do it would be like, where does sine maximize? Well, you guys know that sine is contained between -1 and 1. I mean, we can put this on Desmos. We can look at sine really quickly, okay? Oh, I wouldn't change this to degrees earlier. Okay, anyways, there we go. And you can see that sine never goes higher than 1 and never goes lower than -1, which means that 700 sine x, is like a graph like that. It never goes higher than 700. So I could use 700 right there and I'm good to go. Now, is that like the most approximate? Probably not, but there we go, 700. Now, let's think about the graph real quick here. You guys should know sine starts at 0, and so this is like 700, okay? Now, where does sine hit its peak? Sine actually hits its peak at pi over 2, and then it comes back here at pi. And you should know approximate pi over 2. If pi is 3.14, anyway, it's like 1.57, even if you just knew 1.5. So what is the max? This is a way to get a better approximation between x and c. Well, c is 0, and x was 0.7. So here's 0, and here's 0.7. That's an increasing function the whole time, right? So the max is actually the height at 0.7. And what is the height at 0.7? It's 700 sine 0.7. So you could use 700, or to be even more approximate, we can use 700 sine of 0.7, and I can find it that way. So then I would type it in by going fraction. Make sure I'm in radian mode. I am, okay. 700 sine of 0.7 is where that would max out. And then it's 0.7 to the fifth over 5, boom, factorial. Okay. And this is not a very good error bound, like it's within 0.61, 0.63159. Like that's not amazing, but there we go. All right. Okay, let's look at one more example here. Okay, so here's our last example. The sixth derivative is a positive decreasing function. Find the error bound when a fifth degree polynomial centered at 4 is used to approximate 1. Assume the series converges at 4.1. X is 4.1. Okay? Lagrange remainder, less than or equal to. I just literally write this every time. fifth degree, next term would be sixth, which is why it gave us information about the sixth derivative. I'm going to put z right there. And then it's x minus c to the sixth over 6 factorial. We're always matchy, okay? 6 derivative, 6 exponent, 6 factorial. Match that up. Now, if this is a positive decreasing function, when I'm looking between 4 and 4.1, where is the max going to be? The max is going to be at 4. Now, it didn't tell me anything about the function, so at 4, the max is f of 4, or the sixth derivative at 4, right? Because that's what I'm graphing. So I would just go in here and say, hey, it maxes out at 4, and I don't have any more information, and so that's my answer. All right? So hopefully that kind of explains error approximations. They can be a little bit tricky with the wording and like understanding what you're doing, but there we go. Video under a half hour. Hooray.